What are ensembles in thermodynamics statistical mechanics? Have you ever wondered how scientists predict the behavior of complex systems made up of countless particles? The answer lies in a concept called ensembles. In thermodynamics and statistical mechanics, ensembles are collections of many virtual copies of a system. Each copy represents a possible microscopic state that the system could occupy under specific conditions. This approach helps to connect the tiny behaviors of particles, like atoms or molecules, to the larger properties we can observe, such as temperature, pressure, and entropy. Instead of tracking every single particle, ensembles allow us to use probability to describe how likely the system is to be in any particular state. This makes it easier to calculate average properties over all possible states, which correspond to measurable thermodynamic quantities. There are three main types of ensembles that scientists commonly use, each suited for different situations. The first is the microcanonical ensemble. This ensemble represents an isolated system with a fixed number of particles, a fixed volume, and a fixed total energy. Since the system cannot exchange energy or particles with its surroundings, every microscopic state with the same energy is equally probable. This ensemble is perfect for modeling systems where energy is conserved and unaffected by external influences. Next, we have the canonical ensemble. This one describes a system that can exchange energy with a large heat reservoir while maintaining a fixed number of particles and volume. In this case, the system's energy can fluctuate, but the temperature stays constant due to thermal contact with the reservoir. Different microscopic states have varying probabilities based on their energy, with lower energy states being more likely. This ensemble is useful for studying systems at a constant temperature. Lastly, there is the grand canonical ensemble. This ensemble applies to systems that can exchange both energy and particles with a reservoir. Here, the number of particles, energy, and volume can all change, but the system is characterized by fixed temperature, volume, and chemical potential. This ensemble is ideal for open systems where particles can enter or leave, such as gases in contact with a particle reservoir. Choosing the right ensemble depends on the physical situation and the constraints on the system. However, in very large systems, all three ensembles provide equivalent predictions for average macroscopic properties. The concept of ensembles is essential because it connects the randomness of microscopic behavior with the order we see at the macroscopic level. By calculating ensemble averages, which are the weighted averages of properties over all possible states, statistical mechanics links particle behavior to thermodynamic quantities like entropy and spontaneous processes. In practical terms, ensembles allow scientists to predict how systems behave under various conditions. They can explain how gases expand, how heat flows, or how chemical reactions occur by considering the probabilities of different microscopic configurations. This mathematical framework makes the principles of thermodynamics accessible and applicable to real-world systems with many particles.